Hello, Professor Simmons here. Welcome to PH2011, your first physics course at MSOE. Um, and today we're going to talk about kinematics in one dimension, and that's the basically describing how things move mathematically. And this is in chapter 2 of your textbook. That's not to say that there's not important material in chapter 1. Um, so you're responsible for basically knowing things in chapter 1. It's kind of assumed that you've been exposed to some of that already. There's some important concepts, so I'll just put a note here. There's some important ideas that you need to be fluent with. Things like unit conversions, uncertainty. We'll talk about that in lab. Dimensional analysis, etc. Those concepts appear in an optional homework assignment. So if you have not really dealt with these sorts of things before, work through them in the optional homework and reach out to me, and we can make sure that you get up to speed. So considering I think some students are probably seeing this a lot already, and some may have seen it less, it's going to be kind of our responsibility to get everybody on the same page. Okay, so back to kinematics. The first thing that we need to do is kind of explain and define some terms. So chapter 2 starts with a discussion of something called a frame of reference. So let's and you can think of a frame of reference as basically what you are measuring motion relative to. Okay. So, and I think a good sort of example situation, cartoon situation to consider is that of a moving walkway. It's sort of the minimal example. So imagine, I'll try and draw a cartoon of this. You have a moving walkway. I'll draw depict it like a belt. Try and draw this as neatly as I can. Um, and we can think of a person on the belt. Now, if this moving walkway is moving, that person is going to be moving down the belt. Now, if we put our coordinate system, if we put our frame of reference on the belt, a lot of times we indicate this by just a little coordinate system like this, where it's kind of assumed that this is basically x and y. We put our coordinate system on there, and if it's moving, it's attached to the belt, it would be moving as well. And so the person standing on the moving walkway, standing on the belt, is stationary relative to a frame of reference on the belt. Okay. Now, this is to be distinguished from, let me try and copy this here. In contrast, if instead you imagine your coordinate system not attached to the belt, now the person is going to be moving uh, relative to our frame of reference that's not attached to the belt. Okay. And I think you've probably have kind of an intuition for this. You know, if you're standing next to somebody on one of those, uh, you're not moving. You're, you know, both standing still, even though the thing is moving. But if you're standing next to the belt and people are moving by, they're moving relative to you. So how we can indicate this in drawings a lot of times is we'll do it with arrows. So an arrow is to indicate a vector. So maybe the clearest way to indicate this would be, notice in the upper drawing there's no arrow on the person because they're stationary. It would be a vector of length 0, in other words. Whereas with the second drawing, I put an arrow on them to indicate, okay, they're moving, and they're moving to the right. And so just as sort of an aside, vectors are something that you're going to be responsible for and become really good with in the course of PH2011. And we'll have some material, some review material that's on vectors specifically because it's such an important concept. But you can think of these as numbers with size, and I'll say magnitude, and direction. And we'll get into here in a second some important examples of vectors. So yeah, this frame of reference idea is sort of a foundational idea that's kind of underneath a lot of what we're going to be talking about. So I'm going to be talking about today, so I kind of mentioned it. So some of the other definitions that we need to get into, and I'll point out, we'll make the distinction of which are vectors and which are not. So let me ask you a question. Do you know the difference between speed and velocity? So speed is a scalar and velocity is a vector. So let's make a little chart of some of the different terms. So vector, I mentioned above, numbers with magnitude and direction. Scalars are just numbers with magnitude. They don't have a direction associated with them. So a speed is a scalar. And think of your speedometer. Okay. The speedometer doesn't tell you what direction you're going. It just gives you a number that tells you how fast. Now that's to be distinguished from velocity, which think of like GPS maybe. You could look on your, or if your phone, if your car or your phone or something has a compass that can tell you both the speed and the direction you're going, northwest or something. That combination of speed and a direction is a velocity. Though, maybe this is 60 miles per hour. This would be, or an example of this, 60 miles per hour northwest. Okay. It's got a magnitude and direction. Okay. And we can talk about the actual definition of this is speed is something called distance divided by time. And technically this is an average speed. I'm making a little chart here. Well, velocity is a little bit different. Average velocity, on the other hand, is displacement divided by time. So you're probably wondering, what are these? Oh, and the units for both of these are the same. In our unit system, it's going to be meters per second. But we need to define distance as well. So what are distance and displacement? We need to define those. So distance is just how far. And think your odometer. And of course the units this is in meters. So when you look at your odometer in the car, it's just a number that tells you how far the car has gone. It doesn't tell you, the path or the direction. As opposed to displacement, which is a vector, and it contains information about direction. Okay. So it's, how far in a particular direction. And I'll give you some definitions here in a second, or some examples. So let me try and draw you a cartoon to indicate this distinction between distance and displacement. So we'll consider a couple examples here. Here's an example. I draw a little cartoon. Suppose you you go from your house and you go on a run, and maybe you run around, you run back, you run back to where you started. Now, in this case, let's see, the distance would be 3 miles, but the displacement, which you can depict graphically by drawing an arrow from your starting point to your ending point, your displacement would actually be 0 miles because you're running from home and you return to that spot. Okay? Let me show you another example. So instead, suppose you do you go 5 miles south, you're driving or something. So we'll be thinking about cardinal directions for this example, and then you go 5 miles east. Okay. Now, in this case, what's the distance? And we're just to clarify, we're going to stop there. So the distance in this case would just be, well, 5 miles plus 5 miles. But what about the displacement? Well, the displacement we can find by drawing an arrow from the starting position. If I can draw a straight arrow here. From the starting position to the ending position, or the ending point. In that case, how would you find, the length of that hypotenuse? Let me just clean this up a little bit. Go there. Gotta get used to this pen here. Sorry. You get my drift here. This displacement would be the square root of 5 squared plus the square root of the square root of 5 squared plus 5 squared. You can use your Pythagorean theorem. And you would find that this is about 7 miles. And this would be in the direction, if we're talking about cardinal directions, southeast. Okay. And we could also calculate speed and velocity in a similar fashion. So the speed, if this was in 1 hour, say, or let's do something more interesting than 1 hour. Let's say that this was in 30 minutes. Then this would be a speed of 20 miles per hour, but it would be a velocity of 14 miles per hour southeast. Okay. Where notice we've just done let me be very clear, 30 minutes. So one 10 miles divided by 30 minutes. Here, let me just be more explicit about this. So this would be 10 miles divided by 1/2 of an hour. These aren't really the proper units. We don't work with miles and hours so much, but this is just to give you something that's a little more familiar as we get started. So this would be 20 miles per hour. And then down here we have 7 miles southeast divided by 1/2 an hour. It was 14. Okay. It's just a quick example to show you the difference between distance, displacement, speed, velocity, these scalar and vector quantities. Okay. Let me mention something else. So far, these have all been average quantities. In reality, we can also talk about basically instantaneous versions of this. So what I mean is that let me write it to you. Let's talk about instantaneous versions of these quantities. And to do this, we have to talk about calculus a little bit. So instead of average velocity, so recall with average velocity, what we had just been doing, we said that it's displacement over time. A lot of times we'll indicate this displacement as some x and the time as some interval as some delta time. And we'll use a bar to indicate average. So the little bar over the symbol means it's just an average quantity. Well, the instantaneous version of this, so what does this look like? A change in x over a change in time. A change in something may be reminiscent of derivatives to you, or hopefully that sounds a little bit familiar. So what happens is if we imagine this delta x over delta t as that change in time becomes very small, this average velocity becomes instantaneous. So, or actual, like an actual function. So if we imagine in the limit that the delta t becomes very small, this becomes a derivative, dx dt. So in other words, velocity is the derivative of displacement. And part of why I show you this to you is just that this is a really useful way of thinking about this definition. Because what do you know about derivatives? That's another way of saying it's a slope. Okay. So for example, let me show you an example. This allows us to analyze situations graphically. You might have some plot of displacement as a function of time. And I'll give you just a little example here. And we can interpret this by comparing the slope at these different points. So, for example, if we look at the slope at A, what can we see about it? It's positive. The slope at B, well, it's at the top. Is it changing? Is x changing with respect to time at some point up there? It's not. So the velocity, the instantaneous velocity at the top there at around point B is 0. What about at C? Well, at C, you can see the rise over the run. The slope there is negative. X is getting smaller. And you can also see that this is not symmetrical. At C, it's a little bit steeper than at A. So in other words, the magnitude is larger than A. So what does that mean? It's faster. Okay. So I think this is a calculus-based course. I'll try and, since I suspect kind of everybody is coming from a little bit different math background, we'll work these concepts in, but the expectation is that you're going to need to become fluent with using calculus to solve problems. It's really the language of physics. It makes a lot of things they're simpler to state and less complicated if we use calculus. So we'll work these ideas in as we go. One other definition that I wanted to mention is acceleration. So this would be in our chart up there as a vector. And average acceleration would be the change in velocity over time. And just like we talked about with velocity, acceleration is the derivative of velocity. When we're talking about the instantaneous version. So this is the other definition that we're going to need to make use of. And depending on how familiar you are with calculus, this is another way of saying, recall that velocity was the derivative of displacement with respect to time. So that what that means is that acceleration is the second derivative of displacement. And we can, and I should say the units for acceleration are meters per second squared. So let's look at a little example of using this. Suppose you have a car, a fast car. Whoa. That accelerates from 0 to 60 miles per hour in 4 seconds. So we're going to say we know the acceleration. So this is the case we would just find the average acceleration. So in other words, we're going to divide the change in velocity by the change in time. And to be really explicit, what do we mean by these deltas? We mean v final minus v initial, t final minus t initial. It's a change in something. Well, if it's starting from rest, these would be 0. If we start our clock when it starts to move, this initial time would also be 0. This problem also it involves unit conversions. We have to be able to convert. Notice we want our units to be in meters per second, but we're given this final speed as being 60 miles per hour. So let's convert that. So 60, I'll write it like this just so it's more clear. Miles per hour. We need to convert this into meters per second. So there are different conversion factors that you can use, but one that's handy to remember is that a 5,000 meter race is about 3.1 miles. So what you're doing here is you're multiplying 5,000 meters over 3.1 miles. This is a number that's equal to 1. So we're just multiplying this thing by 1, but it's changing the units. Okay. And we also know that in 1 hour, there are 60 times 60 seconds. So we can cancel our hours. So when we crunch these numbers, we would find that this is 26.9 meters per second. So actually, let me do it like this. This is sort of an aside, converting from miles per hour to meters per second. And then let's divide this 26.9 meters per second by 4 seconds. You can see we'll end up with a unit now that's in meters per second squared. And it's 6.7 meters per second squared. Anything else that I want to mention? So one other graphical example, just to fold in acceleration as well. So I've told you that the acceleration is the slope of the velocity. So suppose we have some x as a function of t graph that looks like that. Well, what would the velocity of this be? If this is displacement, notice velocity is a slope. If this is a line, the velocity would just be constant. And if acceleration is the slope of velocity, if the velocity is constant, what's the slope? The slope would be 0. And you can imagine doing this kind of exercise with all different functions. And if you were to really get into the calculus, you would have to know how to compute the derivatives for those different functions. And we'll do a little bit of that as we go. So hopefully that kind of gets you started with these definitions of distance, displacement, speed, velocity, and acceleration.